Hi everyone, this is video number 7 of our P3 complex numbers lectures. Currently on the screen is page number 20 of P3 tutorial 10 complex numbers. Okay, in this lecture, we will learn about the three primary forms of a complex number. Out of these three primary forms, the first form, the Cartesian form, is what we are already familiar with. A modulus argument form and exponential form will be the new forms to learn in this page. So there are three primary forms in which a complex number can be written. First is a Cartesian form. Okay, so what is a Cartesian form? Cartesian form is the usual x plus yi form that we have been learning in the earlier parts of this chapter. And so when a complex number is written in the form of x plus yi and x and y must be real values, and we say it is in Cartesian form. Okay, so example, z equals to 2 minus 3i, and this is a complex number written in Cartesian form. And of course, your x and y, it must be real numbers under the Cartesian form. Okay, nothing much to discuss about the Cartesian form because this is something that we are already familiar with. Okay, now let's move to the second primary form, which is the modulus argument form. Okay, recall what modulus and argument means. And modulus means the length of the vector that connects the origin to the point representation of the complex number. So in this diagram here, if point capital Z is the point representation of the complex number x plus yi, and then the modulus of the complex number x plus yi will be the length of OZ. It is length of the vector OZ. That is the modulus of the x plus yi. Okay, argument is the angle measured from the positive x direction towards the slanted line. Okay, so here we'll make use of modulus and argument of a complex number to write an alternative form for the usual complex number x plus yi. Okay, so here they tell us to consider the complex number x plus yi. If both x and y are positive, then we'll have such a diagram as printed here, where your point capital Z with coordinates x, y will be in the first quadrant of your Argand diagram. Okay, so from the Argand diagram, we see that if your point Z has coordinate x, y, and then of course, this blue colored number here must be x, and that yellow colored number there must be y. And here x and y must be both positive because our point Z is in the first quadrant, so x and y coordinates must be positive. Now making use of the right angle triangle here, okay, if we set the length of OZ, if suppose that length of OZ, which is the same as the modulus of the complex number Z, or in other words, the modulus of x plus yi, if this length is equals to r, then we can write the vertical side length and the horizontal side length of this right angle triangle in terms of r and theta. Okay, so looking at the right angle triangle, uh, and by the way, the vertical side length must be y, and the horizontal side length must be x. Okay, so looking at this right angle triangle, if we take cos of theta, it will be adjacent side over hypotenuse side, that's x over r. And moving our terms around, x is the same as r cos theta. Okay. Then if we take sine theta, it is opposite over hypotenuse y over r, and after a rearrangement, we have r sine theta equals to y. Okay. Now, the result of x and y in terms of r and theta, it is, although in our diagram here, our point z is in the first quadrant, but I wish to let you know that this result, it hold regardless of which quadrant z lies in. which quadrant the point Z lies in. Right, so even if your point Z happen to be in the second, third, or fourth quadrant, it is still true that the x coordinate must be r cos theta and the y coordinate must be r sin theta. And here, what is your r and theta? Your r is the modulus of the complex number Z. This r here is the modulus. And your theta here is the argument of the complex number Z. Okay, so for example, if your point Z happen to be in the second quadrant, then of course your argument theta must be obtuse. When theta is obtuse, according to ASDC diagram, you'll know your sine of theta is positive and your cos of theta is negative. So if we still use the relationship x equals r cos theta and y equals r sin theta, it would still make sense because since cos of theta is negative, it will make r cos theta the whole thing to be negative. Because r must be positive, r must be positive because r is a length. The modulus is a length. Since r is positive and cos theta is negative, r times cos theta must give you a negative answer. And if you look back at your diagram, it makes sense for the x coordinate of your point Z there to be a negative value. And similarly, for your y coordinate, if you use r sin theta, because sin theta is positive in quadrant 2, it will give you a positive answer for r sin theta, and it makes sense because the y coordinate of point Z in our diagram is indeed positive. You can try to check for the cases where your point Z is in the third and fourth quadrant, it will still make sense. Yeah, so x equals r cos theta and y equals r sin theta is something that you need to know that this results actually hold for regardless of which quadrant your point Z lies in. Okay. Right. So in this two formula or relationship that you need to know, R is the modulus of Z and theta is the argument of Z. Okay. Hence, since we know Z is originally x plus yi, and now we know x is r cos theta, I replace x by r cos theta, and I replace y by r sin theta, and with an I there. And then I can do some rearrangement of terms. I factor out the r, then I will have cos theta plus I sin theta. It is common for people to write I in front of the sin theta rather than sin theta I. Because if we write sin theta I like this, it can be confusing as if you are taking sine of theta times I. But what we really mean is actually sin theta times I at the outside. Right? So if you write sin theta with a bracket and I at the outside, it is actually okay. But for convenience, usually people will just write I at the front. Okay. Right, so Z equals R cos theta, R times cos theta plus I sin theta. And this is known as the modulus argument form. Of a complex number. And so the same complex number, it can be written as x plus yi. It can also be written as r cos theta plus I sin theta, where your r is the modulus of z, theta is the argument of z. Okay, later on page 21, we are going to do a few examples converting between different forms of the complex number. Okay. For now, we just memorize first that the modulus argument form is a form r bracket cos theta plus I sin theta. Okay. For modulus argument form, you have to be very careful that is the cos term that comes first, sin terms comes after. It's always cos plus I sin. It is not sin plus I cos. Sin plus I cos is wrong. It's always cos plus I sin. And also, the symbol in between here, it must be a plus. This one, must be a plus. In order for it to be called a modulus argument form, the sign in between must be a plus. If it is a minus here, then it is not in modulus argument form. This one we have to be very careful. Later on page 22, we will have some examples that tells you on this. Right, the sign in the middle must be plus. It's always cos plus I sign. Right. This strategy down here is just to tell us how to convert from Cartesian form to modulus argument form. Right, to express a complex number in modulus argument form, we only need to find the modulus and principal argument of the complex number. So again, by default, our theta, our argument of z, is given in the principal range, where theta is between minus pi until pi. So in the modulus argument form, we will still, by default, write our value of theta in the principal range. Okay. Then once you have the modulus and argument of the complex number, you just sub the values of r and theta into the form r bracket cos theta plus I sin theta, and then you would get the modulus argument form already. And note that r must be positive because the modulus of a complex number is actually length of a vector, and length cannot be negative. Okay. Right. Next, we move to the third form, which is known as exponential form. For exponential form, we need to know this thing known as Euler or Euler's formula. The correct way to pronounce this word is Euler. But anyway, the name is not important. What's important is you need to know that it's this relationship. E power I theta is always equal to cos theta plus I sin theta for all values of theta. Okay, we are not going to prove this formula because in order to prove this formula, it would require very advanced knowledge in calculus. Okay, so at our current level, we are not going to prove this formula. We will just accept the formula as given. Okay. Okay, so e power I theta is equal to cos theta plus I sin theta. And I believe you notice that cos theta plus I sin theta sounds very familiar to you because it is actually the term that comes in the bracket in the modulus argument form. The cos theta plus I sin theta is exactly over here. Right? So earlier we know that if z is equal to x plus yi, where x and y are real, then we call it the Cartesian form. And then the modulus of z, if we name it as r, and yeah, of course, we know how to calculate r, which is just square root of x squared plus y squared, using the formula for modulus of a complex number. And the theta would be argument of z. And we also know how to calculate argument by following the procedure we learned earlier on page 14. Right, then, yeah, if r is the modulus and theta is the argument, then we know the same complex number z, it can be written in the form r bracket cos theta plus I sin theta. Okay. So over here, we have learned the Euler's formula, which says E I theta is equal to cos theta plus I sin theta. If we multiply both sides by r, then I have r E I theta is r bracket cos theta plus I sin theta. Okay, but this r bracket cos theta plus I sin theta is exactly the same as this thing. Okay, that means the right hand side of our red colored equation, it can be replaced by z. Okay, so notice that this z, and this z is the same z. Okay, is the same z. Okay, and that also means the same complex number z, we now have a third form to write it. So we not only can write it in Cartesian form, which is the form x plus yi, we can also write it in the modulus argument form. And now we have a third form known as the exponential form. So what is this R here? It is still the modulus of Z. It is still the modulus of Z. And what is this theta here? It is still the argument of Z. Right? So the meaning of R and theta in the exponential form is the same as the meaning of R and theta in the modulus argument form. So in other words, once you have the modulus argument form, we can easily convert modulus argument form into exponential form with virtually no effort at all. Because you just have to write it in a different form. The information the two forms require are the same. For example, if you are told that Z is 2 bracket cos pi over 3 plus I sine pi over 3, and then you can easily read that your R is 2 and your theta will be pi over 3. So once you have these two information, you can easily convert the same Z into the form Re power I theta, where your R is 2, E is just a usual E, I is just a usual imaginary unit I, and theta is just pi over 3. Right, so here we have already converted the modulus argument form to exponential form, and it requires zero effort. No work is needed. Because modulus argument form and exponential form require the same pair of inputs R and theta. So once you have modulus argument form, you can extract R and theta and straight away convert it into exponential form. Of course, if you need to convert it the other way around from exponential form to modulus argument form, it is also equally as easy. Right. Okay. So here additional info that is actually not required by syllabus. Just briefly go through this. So when coordinates are theta, usually when we write coordinates, we write it in a form xy, in the usual xy Cartesian plane. For example, this point is x coordinate of 1, y coordinate of 2, we'll write the coordinate as 1, 2. And so x, y is the usual form we write the coordinates, and xy is actually the Cartesian coordinates. Cartesian coordinates. And so there is a different system of coordinates known as polar coordinates, where the coordinate is written in the form r comma theta, where r is the distance of the point from the origin, in other words, modulus of z, and theta is the angle as measured from the positive x direction. So for example, if there is a point which is 5 units away from the origin, and it makes an angle of pi over 4 from the positive x direction, and then its polar coordinates can be written as 5 comma pi over 4. It can be written in the form r comma theta. Yeah. But anyway, polar coordinates is not in the complex numbers. I mean, it's not in P3 complex number syllabus. Right, so you don't have to worry about this. Yeah, this is additional info that is not required by syllabus. However, for further math students, they will learn about polar coordinates in their further math syllabus. Right. For additional info number 2, the modulus argument form and exponential form of a complex number are known as polar forms. And so they are known as polar form because they require the pair of information that is available in the polar coordinates, which are r and theta. And that's why the two forms, modulus argument and exponential form, they can be grouped under the same name known as polar form. Right, so polar form is like the family name for modulus argument form and the exponential form. Right, so both modulus argument and exponential form falls under polar form. Why we call it polar form is because both of these two forms, they require the same information, which are r and theta. And r and theta happen to be the information available in the polar coordinate system. Okay. Yeah, and The reason why we call Cartesian form as Cartesian form is because um, it uses Cartesian coordinates. It uses information which are available in the Cartesian coordinates, which are the usual x, y. Okay. Right. Yeah. Anyway, this additional info is not required in our P3 Chapter 10 syllabus, so you don't have to worry about this additional info. This is just something extra for you to know. Right. Okay. Now let's move to exercise 6. Okay, now converting between the three different forms of complex number is very important in our syllabus. And this is considered to be a very basic skill that the syllabus expects everyone to know. Okay, and you should be able to convert between different forms with little difficulty. Okay. Okay. First, this is converting a Cartesian form into the two other forms. Okay. So you are given z1 equals to 1 minus I. So Cartesian form gives you the information x and y, where x is 1 and y is -1 in this example. To convert the modulus argument form and exponential form, you will need the polar information, which are r and theta. And what is your r? It is actually the modulus of your complex number z1. So modulus of z1 is the modulus of 1 minus I. By the formula for modulus, you have surd of x squared plus y squared. That gives you a surd 2. In pure maths, we always leave the surd as surd form, and we don't convert to decimals unnecessarily. Argument of Z1. So to find argument of Z1, we'll follow the procedure as learned on page 14, where we will visualize the argument diagram in our mind, or you can draw it somewhere at the side. Um, Figuring out which quadrant your point Z1 lies in, it is 1 minus 1, so it should be in quadrant 4. The coordinate 1 minus 1 is here. Your Z1 is in quadrant 4. And this blue colored arrow will be the vector representation of that complex number. Right, so we know this green color angle will be the basic angle, and we are going to take negative of the basic angle as the argument. Basic angle, regardless of which quadrant the point lies in, basic angle is always inverse tangent of modulus y over x. So we'll use that formula here. So we will take negative of the basic angle. Modulus of y over x, y is -1, x is 1, and you get negative inverse tangent of 1, which will give you -π/4. Okay, so once you have your information r and theta, by the way, you don't really need to write out the letter r and the letter theta. You don't really need to write out r and theta. As long as you calculate the modulus, this modulus will be understood as the r, and this argument will be understood as the theta. There's no need to really write out the letter r and the symbol theta. Okay, so with r and theta in mind, we can then write the modulus argument form. Modulus argument form. It will be z1 equals to r is square root of 2 bracket is always cos theta plus I sine theta. When your theta is a negative angle, it is important to put brackets. It's important to put brackets when your theta is a negative angle, or else it might lead to confusion in meaning. If you don't put brackets around your -π/4, it may be interpreted or misunderstood as if you are taking cos, then you minus π/4, which would make no sense then, right? So to avoid confusion, whenever you have a negative angle to sub in as your theta, we always put brackets around the angle. For a positive angle, it doesn't matter if you don't put the brackets. But when you have a negative sign, it's a good practice to put brackets around the angle. Right, so yeah, here is a modulus argument form and exponential form. Exponential form will be easy because it requires the same pair of information, R and theta. The subject is still Z1 because it's the same complex number Z1 written in different forms. I have R is sort of 2, E power I times theta, so it is I times negative pi over 4. It is acceptable to leave it in this form, although it is more common for people to just tidy up the power there and write negative I pi over 4. So both forms which I take here, it can be accepted as at the exponential form. You just write whichever you prefer. Right. Okay, next is question 2. Okay, question 2 gives you the exponential form, and they want us to convert to the other two forms. And so recall that both the exponential form and the modulus argument form, they are under the same category known as polar form, while Cartesian form is actually a separate category. Because polar form require r theta as the information or the input values, while Cartesian form requires the x and y, the xy coordinate on the Argand diagram. Okay, so to convert between exponential and modulus argument form is actually a very easy thing to do. And if you need to convert from polar to Cartesian, it's actually easier to convert from modulus argument to Cartesian. Modulus argument to Cartesian is the easy way to do conversion from polar to Cartesian. To convert from exponential to Cartesian directly is actually very hard to do. Right? Exponential to Cartesian is actually very hard to do. So if you are asked to convert exponential to Cartesian, because it's hard to do, I will advise you to first convert exponential to modulus argument, and then only from modulus argument to Cartesian. Because exponential to modulus argument, this part is very easy to do. So you don't really need any effort here in your conversion from exponential to modulus argument form. Right. Anyway, let's go back to this question here. Z2 is 5e I pi over 3. If you want to make it easier to read what your r and theta is, some people prefer to factor out the I at the power and write the pi over 3 in brackets so that it's clearer that pi over 3 is the theta in the form r e I theta. Then part A, modulus argument form. It will be Z2 equals to, this one requires 0 effort because it's the same r and theta, where r is 5, followed by cos theta plus I sine theta. It's always cos plus I sine. Then your theta here is pi over 3. And pi over 3 is a positive angle, so you don't really need any brackets around it. If you still prefer to put brackets around, it's fine, but it's actually okay to not put brackets here. Right. Then from part B, to convert to Cartesian form, as mentioned just now, modulus argument converting it to Cartesian is actually easier to do as compared to exponential to Cartesian. Since we already have the modulus argument form, we will use this modulus argument form. And what we'll do next is we will compute the numerical value of cos pi over 3 and sin pi over 3. It will compute the numerical values. Okay, so for special angles like 45 degrees, 30 degrees, and 60 degrees, or any other angles associated with these three special angles, for example, 120, 120 is associated with 60 because it leaves an angle of 60 degrees as a basic angle. Yeah, so any angles which is associated with 30 degrees, 45 degrees, or 60 degrees are regarded as special angles. And when we find sine, cos, tangent of these values, the syllabus expects us to give those values in the exact form. Which means if it contains cert, it will write it in cert form. It will not write it in decimal form. Okay. And anyway, cos of pi over 3 or cos of 60 degrees is something that the syllabus expects you to memorize anyway. So cos of 60 degrees, by the way, 60 degrees is pi over 3. 45 is pi over 4, 30 degrees is pi over 6. The cos of 60 degrees is 1/2. Sine of 60 degrees is 3 over 2. And then the next step is just to multiply your 5 into your bracket so that you can write it in the usual x plus yi form. So here's your Cartesian form. Five over 2 plus 5 sub 3 over 2i. And that's it. Okay, now let's move to question 3. Okay, so this one is a modulus argument form given. And because you have some number at the outside, and inside the bracket you have the form cos theta plus I sin theta. When identifying that it is a modulus argument form, remember to check that it is in the form cos plus I sin. The sign in the middle is a plus, and also, of course, your theta, the angles here must be the same angle. It must be the same angle. And then only it is in the modulus argument form. Right. Part A, exponential form. So from the modulus argument form, it's very obvious that the angle theta is pi over 12. R is a 2 at the front. This is your R. Right, so exponential form would require 0 effort. You can write it straight away as Z3 equals to R is 2 EI followed by pi over 12. Okay, then it's okay to leave your answer in this form. Or if you prefer, you can rearrange the power as I pi over 12. For part B, Cartesian form, as mentioned in question 2 just now, it's easier to convert from modulus argument to Cartesian as compared to from exponential to Cartesian. Okay, so we'll use the modulus argument form to begin. 2 cos pi over 12 plus I sin pi over 12. Okay, so cos of pi over 12, this is actually not a special angle. The pi over 12 is not a special angle, so it's okay to write your numerical value of cos pi over 12 in decimal form. And remember to convert your calculator to radian mode. Okay, so you have your 0.96593 sine of pi over 12, 0.25882. But this is your intermediate working. It's not the final answer yet. And so I would advise people to write 5SF to be safe to prevent rounding error. And then the final answer only you convert to 3SF. Okay, for each of your two numerical values. 2 times 0.96593, 1.93 to 3SF, and 2 multiplied into 0.25882, you get 0.518 I, and this is rounded to 3SF, and that's it. Okay. So the Cartesian form, it is Z3 equals to 1.93 plus 0.518 I. Next. Okay, question 4, they give you these few different complex numbers, they want you to convert to exponential form. Okay. Now look at part A. Is it already in modulus argument form? Okay. Modulus argument form needs to be in the form r bracket cos theta plus I sin theta. Okay. Your r can be any positive constant. Inside the bracket, you must have cos followed by I sin. The sign in the middle must be a plus, and of course, your angle must be the same angle. Okay. So for question 4a, is that number there satisfying all these conditions? Okay. You have your 2 being a positive constant in front, so it's a valid r. You have cos plus I sin, which is good. The sign in the middle is a plus, that's also good. And you have your same angle. So it is already in modulus argument form. That means we can just convert it into, we can just say this number is the same as 2ei times pi over 2, and that's it. You can convert this number into exponential form straight away. Okay. For part B, this one is tricky. Okay, so this number, it appears as if it is in modulus argument form, but actually it is not. Because although you have cos followed by I sin, you have the same angle pi over 3, but the problem is the sign in the middle is not a plus. This is not a plus. Therefore, this entire number here is not in modulus argument form. So you cannot read your r and theta yet. When the number is not yet in modulus argument form, you cannot read the r and theta. So how to fix this problem? How to convert it into modulus argument form? And so you need to recall from trigonometry that cos of minus theta is the same as cos theta for whatever value of theta. And sine of negative theta is the same as negative sine theta. When we learn the trigo chapter, I used to say that cos can swallow away the negative in the angle, and sine can pull out the negative. Okay, so here we are going to use these two properties in the reverse direction. Okay. To make it more obvious, I will do a bit of rearrangement of terms here first. Okay. This cos pi over 3, I still write it here. Here I convert it to a plus, but I move the negative to stick with the sine term. So I write plus I times minus sine pi over 3. So it's still the same as the previous line. My latest line here is still equal to the previous line because I'm just shifting the negative and stick it to the sine term. Okay, now I want to apply the properties in purple on the right of your screen from right hand side to left hand side. Okay, so cos of theta, it can be written as cos of minus theta for whatever value of theta. And so here cos of pi over 3, it is the same as cos of minus pi over 3. And then negative sine of pi over 3. Negative sine of pi over 3. If I take theta to be pi over 3, then this must be the same as sine of minus pi over 3. Okay, so I go from right to left. I go from right to left. So I write this as sine of minus pi over 3, close and close and close. Now to make it more obvious to everyone, I will just write one more line of working here. And where I remove one layer of the blue color bracket, and this is the same as I sine minus pi over 3. And then now it should be very clear that your number now satisfies the modulus argument form. because you have a positive constant at the front. Inside the bracket, you have the form cos followed by I sign. You have a plus in the middle, and you have the same angle. Right? Then this is now in modulus argument form. Right? So we can then write it into exponential form using square root of 2 as the r. E power I and theta would be the negative pi over 3. Okay, then it's good enough to leave your answer in this form. If you prefer, you can proceed further to just make the power of E look nicer. You can write as negative I pi over 3. It will be the same. So either this or this, it will be acceptable as the final answer. Right. Now let's move to question C. Question C is just a single number 5. Question C is just a single number 5. And how do we convert it into exponential form? Okay. Well, we know the exponential form. The exponential form needs to be in the form REI theta, okay, where your R needs to be a positive real value or positive constant. Your theta, it just needs to be some angle between. Angle in the interval, or okay, maybe I say it this way, is angle that satisfies this inequality, theta between minus pi to pi. Okay, so the easiest way to do question C here is to realize that 5 can be written as 5 times e power 0, because e power 0 is just 1. Then I can also write 0 as I times 0, because I times 0 is still 0. But now 5ei0 is already in the exponential form. You already have your 5 as the r. The positive constant that you need is 5 there. And then you have e followed by power I times 0. And 0 is a value somewhere in between negative pi to pi. So it is a valid principal argument. H0 is a valid principal argument. So this is already in exponential form. Okay, so we are done here. Okay. An alternative way to do the same question C is to notice that from the Argand diagram, the real value of 5 will be a point on the real axis. This is the point representation of the number 5. And so the vector representation will be the vector that connects the origin to the point representation. And if you measure the angle made between the positive x direction and this black colored vector, it is 0 as the angle. Therefore, the argument of the number 5 is 0 radians. And modulus of 5, it will be the length of the black colored vector, which is obviously 5 units. And from there, you can take 0 to be theta, 5 to be r, and then you can write 5 to be REI theta. Okay. Then it will still end you up with the same answer. Okay, so this is the alternative method to do it. Right. Question 4 is done. Now we'll move to the bottom part of page 21. Multiplication and division of two complex numbers in polar form. Okay, so let's talk about modulus argument form first. Okay, so when we multiply two complex numbers, okay, so here if z1 is r1 times cos theta 1 plus I sin theta 1, and z2 has modulus of r2 and argument of theta 2. And so here they're actually telling us that modulus of z1 is r1, argument of z1 is theta 1. Then they just write it in modulus argument form. And from here, they are telling us mod of z2 is r2, and argument of z2 is theta 2. Okay, so then from the modulus argument form, if we do multiplication, if we do z1 times z2, it will be your r1 bracket cos theta 1 plus I sine theta 1, followed by r2 cos theta 2 plus I sine theta 2. Okay. Now, if we try to tidy up this messy looking expression, what we can first do is to group your r1, r2 at the front. And then you have your cos theta 1 plus I sine theta 1 multiplied by cos theta 2 plus I sine theta 2. Okay. R1, R2 stays at the outside. And now I want to expand the two brackets at the back. Okay, I know that this and this combination will eventually give me the real term. So I take cos theta 1 times cos theta 2 plus I squared sine theta 1 sine theta 2. Because theta 1 and theta 2 are different angles, we cannot write as cos squared theta. We cannot write as cos squared because theta 1 and theta 2 are different angles. Okay? And by the similar reasoning, we are not allowed to write sine squared theta here because theta 1 and theta 2 are different angles. Right. Now, the other two combinations, this and this combination, will give me the term that contains I. Okay, so I also group them together. I have the outer combination gives me I cos theta 1 sine theta 2. Okay, and the inner combination gives me I sine theta 1 cos theta 2. Okay, next, I squared, I will replace it by -1. Cos theta 1 cos theta 2. I squared becomes a negative sine theta 1 sine theta 2. Okay, while the yellow colored terms at the back, I will just factor out the I and I move this term to the front. Okay, I write sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. Okay, now recall your trigo identities. Okay, recall your trigo identities. Okay, right at the top right corner of your screen. Okay, recall that cos of A plus B is cos A cos B minus sine A sine B. And then you notice that these terms in dark blue, they have the form cos A cos B minus sine A sine B. And so that's why when we learn the trigo chapter in P3, I keep emphasizing that it's important for you to memorize the trigo formula, so that you can identify when is the occasion to apply the trigo identity formula from right hand side to left hand side. If you don't memorize the trigo formula, it will be hard for you to identify that here we actually have a situation where we can apply the trigo formula in the reverse direction. And so we do have the form cos A cos B minus sin A sin B, which we know if we apply the trigo identity from right to left, you will end up having just cos of A plus B. Then also recall that sine of A plus B is sine A cos B plus cos A sine B. If you look at your red colored terms in bracket, they do have the form sine A cos B plus cos A sine B. Which means if you apply the triple identity in reverse direction, it will just be simplified to sine of A plus B. Okay. Now let me continue with my working here. I have R1, R2. The underlined black colored terms, they will just simplify to become cos of A plus B. While the red colored terms, they will just become I times sine of A plus B. Sorry, I should have written theta 1 and theta 2, not A and B. Theta 1 and theta 2. And this is theta 1, theta 2. Okay, so look at our latest result at the bottom of your screen. So we actually have a modulus argument form where the number at the front, R1 times R2, it is just some positive real number. And because R1 itself is a positive real number, R2 is also a positive real number. So R1 times R2 is just another positive real number. And inside the square bracket, you have cos followed by I sign, you have plus in the middle, and you have the same angle. Right, so this is the modulus argument form. This is the modulus argument form, and from this modulus argument form, you can read the new modulus and the new argument. Okay. So here, what is your new modulus here? New modulus will be R1, R2, the positive constant at the outside of the square bracket. Your new argument, it is theta 1 plus theta 2. It is the common angle in both the cos and sine terms. But what is actually your new modulus here? On the left of your equation, at the very top left corner, it is Z1, Z2. So the new modulus is actually the modulus of Z1, Z2. And the new argument is actually the argument of Z1, Z2. So as a summary, if we have modulus of Z1 is R1, modulus of Z2 is R2, then modulus of Z1, Z2, it is simply just R1, R2. So this is a general result. And also, if your argument of Z1 is theta 1, argument of Z2 is theta 2, then argument of Z1, Z2, and by what we had just obtained earlier, it is theta 1 plus theta 2. And that means when we multiply two complex numbers, we just need to multiply the modulus. Multiply the modulus and add the arguments. In fact, this is also consistent with the properties of modulus and argument that we have learned earlier in this chapter on page 15. So if you recall the properties of modulus and argument earlier, we know that mod of Z1, Z2, modulus can be distributed over multiplication, and you still get R1 times R2. Then argument has the similar property as logs, and so you can break this up as argument of Z1 plus argument of Z2, and you still end up having the same result, theta 1 plus theta 2. And so this is consistent with whatever that we have learned earlier in this chapter. Okay. So this is just to This is just to emphasize on the fact that when we multiply two complex numbers, we just need to multiply their modulus to obtain the new modulus, and we just need to add their arguments to obtain the new argument. When it comes to division, I already expect what the result will look like. Since you know this would be consistent with the properties of modulus and argument that we have learned earlier on page 15. And so we know that mod of R1 over, mod of Z1 over Z2, modulus can be distributed over division. So you will get R1 divided by R2. So R1 over R2 will be the new argument here. New modulus here. While your new argument, if you find argument of Z1 over Z2, by applying the properties of arguments similar to logs, you have argument Z1 minus argument Z2, and that would be theta 1 minus theta 2. So this is where they obtain the new argument. If you want to try to prove it using trigonometry, it can also be proven, which I will now just quickly go through the proof. Proof using trigo. Z1 over Z2, it will be R1 times cos theta 1 plus I sine theta 1. Z2 is R2 cos theta 2 plus I sine theta 2. R1 over R2, I will just group them together at the front. And then this fraction at the back, this fraction at the back, I'm going to multiply by a fraction with the same numerator and denominator, where the same number that I will put at the top and bottom is the conjugate of the denominator here. It's just like how we would usually simplify a division by a complex number. So I will take cos theta 2 minus I sine theta 2. This is take the conjugate. And then of course I need the same number above. R1 over R2 is still at the front. Now the two fractions at the back, I will multiply them horizontally. At the bottom, I have a product of a conjugate pair, which I know the result must be x squared plus y squared, where the x is cos theta 2. And so x squared will be cos theta 2 whole thing squared. Y is the coefficient of I in either one of these two complex numbers. So I'll just take sine theta 2 squared. So I have the x squared plus y squared. Yeah, if you had taken negative sine pi over 2 to be the y here, it will have the same result. Because the negative will disappear anyway when you have a square at the front, when you have a square at the outside. Right. Then at the top, at the numerator, I know there is this and this combination that will generate the real term. So I have cos theta 1 cos theta 2 minus I squared sine theta 1 sine theta 2. Okay, then I also need two more combinations, the inner and outer combination. Okay, and this will give me the imaginary term. Okay, I write the inner combination first this time. Sine theta 1 cos theta 2 and minus. I is already written outside of the bracket, so what I need here is just cos theta 1 sine theta 2. You have stand my line and close my bracket. R1 over R2. At the bottom of the fraction, it is just cos squared theta 2 plus sine squared theta 2. When we have cos squared plus sine squared of the same angle, we can apply identity, and we know this would become just a 1. As simple as that. Then at the top, I know I squared is -1, so negative I squared will become just a plus symbol. Cos theta 1, cos theta 2 plus sine theta 1, sine theta 2. The thing at the back, I will just copy it back for now. Okay. Now observe that this terms in yellow, it has a form cos A cos B plus sine A sine B. Okay, so I know I can apply trigo identity and just simplify it to become cos of A minus B, where A is theta 1 and B is theta 2. Cos A cos B plus sine A sine B, it simplifies to become cos of A minus B. Okay, while the terms that I'm coloring in pink here, it has a form sine A cos B minus cos A sine B. This one can be simplified to become sine of A minus B. So I have plus I sine of A minus B, where A is theta 1, B is theta 2. Okay, the bottom is just number 1. So I have R1 over R2 cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay. So again, check whether this is a modulus argument form. You have a positive constant in front because R1 and R2 are both positive constants. They are positive real constants. So R1 over R2 must also be a positive real constant. Then you have cos followed by I sine, you have plus in the middle, and same angle. Right, so this is already in modulus argument form. Therefore, you can extract R1 over R2 as the new modulus, and the common angle of the cos and sine term to be the new argument. And what is the complex number that we are working on? We are working on Z1 over Z2. Okay, so this is actually modulus of Z1 over Z2, and this new argument is actually argument of Z1 over Z2. So this is how we prove it by trigonometry. Okay, so as the summary, what we realize from here is that when we divide two complex numbers, we just need to divide their modulus. Okay. If you want to find modulus of Z1 over Z2, you just take R1 over R2, where R1 is a modulus of Z1, R2 is a modulus of Z2. If you want to find argument of Z1 over Z2, we just need to subtract their individual modulus. So it just becomes theta 1 minus theta 2. And of course, these results, which I'm circling on the right of your screen, is consistent with the properties of modulus and argument we learned in page 15. Okay, so moving on to exponential form, this will be even easier to understand because this is just an application of the law of indices. The result we have here for exponential form is of course consistent with the result we have for modulus argument form. Okay. So if Z1 has modulus R1 and argument theta 1, Z2 has modulus R2 and argument theta 2, and then you can write your exponential form as this and this. And then when we multiply Z1 and Z2, this one is very straightforward. It becomes R1 EI theta 1 times with R2 EI theta 2. Then if I group my R1, R2 together and the exponential terms together, then for the two exponential terms, I have indices of the same base multiplied together, so I can add up the powers I theta 1 plus I theta 2. and then R1, R2, EI bracket theta 1 plus theta 2. And this is actually in exponential form. This is in exponential form, where R1, R2 becomes your new modulus, or the so-called new R, and this is actually your new theta. Then if you compare this with the result we had in modulus argument form earlier, it would be actually the same result, where your R1, R2 is a new modulus, and your theta 1 plus theta 2 is a new argument. It will be consistent. It's the same result. Just that for exponential form, it's actually even easier to derive it. Okay. Then for division, Z1 over Z2, it becomes R1 EI theta 1 divided by R2 EI theta 2. Okay, then if I group my R1 over R2 together, then I would have division of indices of the same base. Then, wait, I shouldn't have an equal here. Okay. Then I can subtract the powers because I'm having division for indices of the same base. Then upon factoring out the I from the power, I mean at the power, I factor out the I. Then this would become the new R, or the new modulus. And this part will become your new argument. Okay. And so when we divide two complex numbers, when we take a complex number, divide by a second complex number, we just need to divide their modulus and subtract the argument. Okay. And the summary is given below here in these two sentences. And so when we find the product, or when we multiply two complex numbers, we just multiply their modulus. This moduli is just a plural form of modulus. They just multiply their moduli and add their arguments if we are multiplying two complex numbers. If we are dividing two complex numbers, then just divide the moduli and subtract the arguments. Okay. Okay, next, on page 22, de Moivre's theorem. Okay, so de Moivre's theorem is applicable only for the polar forms, namely the modulus argument form and exponential form only. And de Moivre's theorem is not applicable for Cartesian form. So according to de Moivre's theorem, for all real values of n, we have the following result. Okay, so they say if you have cos theta plus I sin theta to the power of n, the power n can be just multiplied into the angle theta, giving you n theta straight away. Okay, so this is a very powerful property. It's a very powerful property because usually things are not so easy. Like, if you have sine theta to the power of n, it is in general not the same as sine n theta. It's in general not the same as sine n theta. And similarly, cos theta to the power of n is not the same as cos n theta in general. But here, when you have cos theta plus I sin theta whole thing to the power n, you have this very convenient result here, where your n can just be distributed into the angle straight away. Then for exponential form, it's even easier to understand because it's just law of indices. So if you have e power I theta, whole thing taken to the power n, you can just multiply the powers together. EI theta to the power n, you can just write as EI theta n, and just rearrange your terms at the power there, you have n theta. Okay, so you have this very convenient result. Okay. Right, so the sentence at the bottom here says, note that the de Moivre's theorem in exponential form is simply a statement of one of the laws of indices. Because we are simply just applying law of indices where we multiply these powers together. Okay. So just a very quick proof of the case n equals to 2 using the modulus argument form. So Oh, and by the way, in the two boxes of results here, um, notice that I don't put the R there. Well, if you put the R there, here, maybe I should just show you what the result will look like if R is not 1. And so this is actually for the case R equals to 1. For case R equals to 1, this is also the same for the case R equals to 1. Okay, so what if the R is not 1? So in general, if we have R bracket cos theta plus I sine theta, taken to the power n, you just need to distribute your n to your R and to this bracket, R power n cos theta plus I sine theta to the n. And then using the result in the printed box, you can distribute your n into the angle theta. Then you straight away get R to the n cos n theta plus I sine n theta. And similarly for exponential form, if I have R e I theta taken to the power n, and then n gets distributed to the R and the e term. So I have R n e I theta n, and I have R n e I n theta. And just by applying the result here. Okay, now just a very quick proof of the result in the printed box for the modulus argument form for the case n is 2. And just to show you how can this be proven using trigonometry. So for the case n equals to 2, the result in the printed box for the modulus argument form, it would look like this. Cos theta plus I sine theta to the power of 2, it would be equal to cos 2 theta plus I sine 2 theta. Okay, now here is the proof using trigo. I start from the left-hand side, cos theta plus I sine theta power 2. Okay. So I expand this quadratic as usual. So I have cos squared plus I sine theta holding squared plus 2 times cos theta times I sine theta. Cos squared plus I squared sine squared plus 2I. Maybe it's better for me to write I at the front. I bracket 2 sine theta cos theta. I squared is just a negative 1. And so I write as cos squared minus sine squared theta. And the term at the back, I keep it as I 2 sine theta cos theta. Okay, cos squared minus sine squared. This is one of the double angle formula for cos 2 theta. And recall from the trigo chapter. And then 2 sine theta cos theta, that is actually sine 2 theta. And there we have it, cos 2 theta plus I sine 2 theta. Okay, so this is how you can prove using trigo. Of course, when the power n is 3 or higher, the proof will be more and more tedious, and we will not go through those. Okay, so I'm showing you the proof using trigo for the case n equals to 2, and just to show you that it's actually consistent with our trigonometric formula. The results that we have here is consistent with all the trigo formula that we have learned earlier. Okay. Now, example 5, without using a calculator, find the value of cos pi over 3 plus I sin pi over 3 to the power of 3, giving your answer in Cartesian form. They don't allow us to use a calculator. Okay. Right, so your cos pi over 3 plus I sin pi over 3. At first, you should check whether the cos theta plus I sine theta term is in the modulus argument form or not. So here you have cos followed by I sine. And so according to the result that is given under the Moivre theorem, as long as you have cos theta plus I sine theta to the n, you can write as cos n theta plus I sine n theta. Okay. So do we have cos theta plus I sine theta here? You have cos followed by I sine, you have plus in the middle, you have the same theta. Okay. So you can confidently apply the Moivre theorem. Okay. So when the 3 gets multiplied to the pi over 3, and now you have cos pi plus I sine pi. They say give your answer in Cartesian form, so you will just convert your cos pi into the numerical value of -1. Sine pi is just 0. That gives you simply just -1, and we are done. Next, example 6. Without using a calculator, find the value of sine pi over 3 plus I cos pi over 3 to the power 4, giving answer in Cartesian form. Note that this is sine plus I cos. According to the Moivre's theorem, when you have cos theta plus I sine theta to the n, then only you can apply the Moivre's theorem to distribute your n to the angle. But when we have when we have sine plus I cos, the Moivre's theorem cannot be applied. It cannot be applied. So we have to think of a way to convert the expressions in the bracket into the form cos plus I sine of the same angle. Okay. Okay, so here, the note or the hint here tells you that you can use the complementary angle identity that you have learned before in the trigo chapter. Let's recall that sine of pi over 2 minus theta is the same as cos of theta. Cos of pi over 2 minus theta is the same as sine of theta. And we have a complementary pair in between sine and cos. Okay. Right, so this would allow us to change the sine term to the cos term and change the cos term to the sine term. Because you actually need cos to be the real term and sine to be part of the imaginary term. Okay. So it would be good to change sine to cos and cos to sine, and we can do that by applying the complementary angle identities. So if you take theta to be pi over 3, then you have sine pi over 3 will be the same as cos of pi over 2 minus pi over 3. And from the first formula here, if you take theta to be pi over 3, then cos pi over 3 is the same as sine pi over 2 minus pi over 3. Okay. Now let's do that. Okay, so first I copy the question first, sine pi over 3 plus I cos pi over 3 to the 4. Sine is converted to cos, then I have to take pi over 2 minus the original angle. Cos converted to sine, then again I take pi over 2 minus the original angle. Power 4 is still at the outside. Okay. Pi over 2 minus pi over 3 should give me a pi over 6. I sine pi over 6 to the power 4. Okay, now can we apply the Moivre's theorem? Do we have the form cos theta plus I sine theta? Yes, we do have, because we now have cos followed by I sine. We have plus in the middle. We have two same angles here. Okay, so we can confidently distribute the 4 into the angles. Okay, so now you have cos of 4 pi over 6 plus I sine of 4 pi over 6. Okay, 4 pi over 6 can be simplified to be 2 pi over 3. They don't allow us to use calculator, so we should do the calculations of cos and the sine terms manually. 2 pi over 3 is not an angle in quadrant 1. 2 pi over 3, if you visualize it in the ASTC diagram, is actually a quadrant 2 angle. 2 pi over 3 is actually 120 degrees. And so that leaves you with pi over 3 or 60 degrees as the basic angle. Right, so according to ASTC diagram, cos of 2 pi over 3 can be written as sine of pi over 3, sine of the basic angle. Do we need a negative in front here? Check your ASTC. Second quadrant. I meant a cos here. Yeah. And so cos of 2 pi over 3 can be written as cos of pi over 3. We need a negative here because in the second quadrant, only sine is positive, cos should be negative. Then I have a plus I. Here, sine of 2 pi over 3 can be written as sine of the basic angle. And we do not need any negative here because in the second quadrant, sine is supposed to be positive. Then let's compute negative of cos pi over 3 will be negative of 1/2. This is sec 3 over 2. And yeah, just write it in a more familiar form. Sec 3 over 2I at the back. Okay, done. So this is Cartesian form as a final answer. Okay, so applying by the de Moivre's theorem, it will make things much more easier. Or else you will have to take the power of 4. If you take to the power of 4 using the traditional method, by using binomial expansion, it will be very painful to simplify later on. Okay, now let's go to example number 7 on the next page 23. Without using a calculator again, I find the value of cos pi over 4 minus I sine pi over 4 to the 6, and giving an answer in Cartesian form. And so before you apply the Moivre's theorem, always check whether it is in the correct modulus argument form or not. And so the correct modulus argument form here, for the case when r is 1, then it must be cos theta plus I sine theta. But the problem here is we don't have a plus in between, it's a minus here. So we'll have to modify it a bit so that it matches the form cos theta plus I sine theta. So we'll apply the properties of negative angles again. Cos of pi over 4 is the same as cos of minus pi over 4. And maybe I do it a bit slower. Cos of pi over 4, I will keep it that way first. Then I will write as plus I negative sine pi over 4 so that it's more obvious what I'm doing. Okay. Okay. Then cos pi over 4 I replace by cos of minus pi over 4. Then sine of pi over 4 I replace by sine of minus pi over 4. And this is by applying the properties cos of minus theta is the same as cos theta, and sine of minus theta is the same as minus of sine theta. Okay, I'm applying these two properties here. Okay. Now I have the form cos plus I sine. Cos plus I sine, I have a plus in between. I have the same angle. Okay, then now we can apply the Moivre's theorem, where the power 6 can now be happily distributed. Cos of minus 6 pi over 4 plus I sine minus 6 pi over 4. 6 pi over 4 is just 3 pi over 2. Okay, so when we have a trigo function applied to an angle, so in general, cos of theta, it must be the same as cos of theta plus 2 pi. Sine of theta must also be the same as sine of theta plus 2 pi. Because when we add any angle by 2 pi, it still ends up having the same direction in the same quadrant. So that's what I will do here. Minus 3 pi over 2, I add by 2 pi. right? To make the angle become an angle in the first positive cycle, plus by I sine minus 3 pi over 2 plus 2 pi. So now I have cos of pi over 2 plus I sine pi over 2. The cos of pi over 2 is a value that we memorize as 0. Sine pi over 2 is 1, so you end up getting a single I, and that's it. Okay. So next, example 8, which is also the last question that we'll discuss in this video. Use the Moivre's theorem to evaluate this uh, fraction with very high powers, giving an answer in Cartesian form. Yeah, so this is a kind of question where the Moivre's theorem will be very useful, or else it will be such a pain to simplify the thing. Okay. So, remember that the Moivre's theorem, it can only be applied to polar forms. It can only be applied to polar forms which are exponential and modulus argument form. The Moivre's theorem cannot be applied to Cartesian form. Okay. The problem here with this question is that the complex numbers that we have, the 1 plus I, 1 minus I, they are in Cartesian form. These are in Cartesian form. So we cannot apply the Moivre's theorem yet. And also, we wouldn't want to expand the power 11 and power 9 using binomial expansion because it will be such a pain to simplify. Okay, so if we want to apply the Moivre's theorem, we must first convert 1 plus I into either modulus argument form or exponential form first. Okay, so 1 plus I. Okay, I need the modulus and argument of it. Okay, so modulus of 1 plus I, it is a surd of 1 squared plus 1 squared, that gives a surd 2. Argument of 1 plus I, if you visualize the Argand diagram, the point 1, 1 is in the first quadrant. So we just take the basic angle itself as the argument. So it's inverse tangent of 1 over 1. That gives me pi over 4. A basic angle is inverse tangent of modulus y over x. Therefore, 1 plus I can now be written as, I choose to use the modulus argument form here. So it will be r times cos theta plus I sine theta. Okay. And now, since we already have the modulus argument form, we can then take power 11 on both sides. 1 plus I, it will be this whole thing on the right hand side, taken to power 11. I mean power 11 also on the left. So I'm taking power 11 on both sides. Therefore, this becomes surd of 2 to the power of 11, and cos pi over 4 plus I sine pi over 4 power 11. We know when we have cos theta plus I sine theta to the power n, that power n can be distributed into the angle straight away. Surd 2 power 11, that will give me, well, surd 2 power 11. One quick way to simplify it manually is that you can treat this as surd 2 to the power of 10 times surd 2. And surd 2 to the power of 10 is the same as 2 to the power of 5. Because surd 2 is 2 to the power of half. Yeah, and then you can easily get this as 32 surd 2. Okay, so I write 32 surd 2 here. Okay. Then cos of 11 pi over 4 plus I sine of 11 pi over 4. Okay, 11 pi over 4 is already beyond the first cycle. It is already more than 2 pi. So I will reduce it by 2 pi. Reduce the angle by 2 pi because I have a cos and sine applied to the angle. And so I can confidently reduce it by 2 pi, and I'm sure that the value will remain unchanged. Okay. Then this will become cos of 3 pi over 4 plus I sine of 3 pi over 4. 3 pi over 4 is an angle in quadrant 2, leaving you a basic angle of pi over 4. And that means cos of 3 pi over 4 can be written as cos of the basic angle. Cos of the basic angle, possibly with a negative in front. So do we need a negative? Refer to your ASTC. The second quadrant is S, so you need a negative in front of the cos. And I think I will not simplify this further. I will not simplify this further. I will just leave it in this form first. Yeah, it's actually better. It's actually better to leave it in this form first because later we still get to divide the 1 minus I power 9. So I will just leave it in this form first. After doing the division, then only I simplify at the end. I think that would be better. Okay. Now the next number is 1 minus I to the power 9. And so, I mean, the number at the denominator of the question is 1 minus I to the power 9. So I would want to convert 1 minus I to the modulus argument form first. And so the modulus is 1 squared plus minus 1 squared. So again, I get a square root 2. Argument of 1 minus I. If you visualize the Argand diagram, 1 minus 1 is in quadrant 4. So I would take negative of the basic angle, inverse tangent of modulus y over x, that's minus inverse tangent of 1, that's minus pi over 4. Okay. Now I can write 1 minus I as the modulus argument form, sub2 cos theta plus I sine theta. Okay, then when I apply power 9 to both sides, I will get sub2 to the power of 9 cos of minus pi over 4 plus I sine of minus pi over 4 to the power of 9. Z2 to the power of 9, it is just 2 power 4 times Z2, which is 16 Z2. Then the power 9 by the Moivre's theorem, I can distribute it. Because I already have the cos theta plus I sine theta form inside the square bracket. And so I can happily apply the Moivre's theorem. This now gives cos of minus 9 pi over 4 plus I sine of minus 9 pi over 4. Okay, let's see. Okay, I'm not going to simplify this any further. I will proceed to do the division. Okay. So the question is 1 plus I to the 11 divided by 1 minus I to the 9. Okay, 1 plus I to the 11 is this purple colored number here. So I will just put it down here as 32. So 2 cos of 3 pi over 4 plus I sine of 3 pi over 4. 1 minus I to the 9, it is this thing here. I have 16 Z2 cos of minus 9 pi over 4 plus I sine of minus 9 pi over 4. So what we have here is actually a division of two complex numbers. You have one complex number divided by the other, and both of these numbers are in modulus argument form. You have uh, a real positive constant at the front. Then inside the square bracket, you have cos plus I sine, cos plus I sine. Then you have same angle at the top, same angle at the bottom. And so these are complex numbers in modulus argument form, being divided. And so you can just apply the result that we have learned on page 21, saying that you just need to divide their individual modulus. So 32 is a 2 divided by 16 is a 2 simplifies to become just a 2. A 2 becomes a new modulus, while the argument, it will be 3 pi over 4 minus negative 9 pi over 4. Cos plus I sine of the same angle. Because of you would need your answer to also be in modulus argument form. And when you apply the result on page 21. Okay. So what do we have as the angle here? You have 3 pi over 4 plus 9 pi over 4. That gives you 3 pi. Okay, but we know we can always subtract by 2 pi. Okay, so you have 2 cos pi plus I sine pi. Okay, cos pi is negative 1, sine pi is 0. Okay, so we end up having just a negative 2. Okay, and we are done. Okay, this is our final answer in Cartesian form. Okay. Well, actually just now, when I did my 1 plus I power 11 in purple color, uh, I could have left my 1 plus I power 11 in this form. Okay. We can actually leave it in this form. Okay, and then you can bring it down here when you do the division. So it's not a must to do the last two lines in purple color. It would still work that way. And because as long as you have modulus argument form at both the numerator and the denominator, then it would be easy to do the division. Yeah, so that's all that I would want to cover in this video. I'll continue with page 24 in the next video.